notes, complete, you don't really need to listen to me talk about just computing those variations. Anyway. All right, so just to sort of recap where we were, I'm going to write the two momentum equations in the current configuration and the reference configuration that we derived last time, but I'm going to write them the equilibrium form, so like no acceleration terms, okay? So, and that doesn't change anything that we're developing today. Really, it's just, I guess, me being a little bit lazy, because for review here, right? So, in the current configuration, we had this, where rho is equal to rho s plus rho f, because remember we added the two individual equations together, and we have the boundary condition traction vector on the boundary is equal to so this is in the in the current configuration. And I guess I'll leave that. And so then in the reference configuration we have it's just the pullback of the other equation. Well, now this is the gradient with respect to big X. And the traction vector on the boundary looks like that, where we've pulled back so the current configuration equation we derived by basically, because we derived all the equations in the current configuration. Remember, all the integrals of the variations were in the current configuration. So that first equation we got by just summing the two species equations together, the solid and the fluid. And then the second equation we got by pulling back to the reference configuration of the solid, right? So that's why you have JSVS, right? And we'll see why that's relevant, why we chose to do that when we look at the conservation of mass. So we want to allow mass flux in and out of the solid, right? And so yeah, these are in the reference configuration.